So the subject of my lectures will be QCD strings. Well, and the main goal of these lectures was defined to me by Eliezer, who told me that basically I should achieve that the students who come here come out as different persons. And well, I think it's achievable. I started thinking about this subject roughly 10 years ago, and I changed quite a bit over those 10 years. So I presume if I compress that information which I learned over the time in for lectures, then I'll achieve the same goal with you. But the plan is the following. So roughly speaking, should I put it lower?
Lower.
Yeah.
Maybe it's further it is from the mouse
and take off the Mac.
And the Mac should be removed for interference
Okay.
effect.
Okay, good. So the plan is roughly speaking the following. So I'll start with discussing long strings and with IR story. Then I will talk about long strings UV story, or rather an attempt of the UV story, but somewhere in between there will be short review kind of experiment where experiment here means mostly numerical simulations of QCD, or rather pure glue on the lattice. And finally, time permits, I will also talk about short strings. Now to achieve the goal which Eliezer posted to me, I decided to take a shortcut. My understanding that most of the students here, they have string theory background. So what you need to do now, you need to pretend that you know nothing about string theory, and that you are kind of very down-to-earth effective field theorist. That you are completely ignoring what string theorists were doing. Well, that will help me to achieve the goal to change your persona in these lectures, but also it will put you roughly at the same initial conditions where I was 10 years ago. And then you want to ask the following question. So basically, the only thing you vaguely heard from string theorists is that something special happens when you study strings in 26 dimensions. Okay. So the question I want to ask is the following. So let's say you have some quantum field theory. Our main example and main goal will be to talk about QCD. But it doesn't have to be QCD. It could also be a billion Higgs model, for instance. So you have a string, you have quantum field theory which exhibits string-like objects. So in the QCD context, or rather in pure glue context, I'm thinking about kind of one can introduce fundamental pair of non-dynamical fundamental quarks, and then there is a flux tube between them, or in the context of a billion Higgs model, we have kind of cosmic strings or abricos of Nielsen-Olsen vortices, and well, you can study these objects. One of those objects can be in this room, so you can study long string like this, and you study them as a low energy effective field theorist. And so the question is, when will you notice that something special happens when d equals to 26? So at what point you will see that there is some miracle happens there. And well, apart from achieving the goal posed by a laser, there are two other purposes. I'll start, well, actually three other purposes. I start with this question. First, that's how I entered into the subject. That's my initial data. But also, well, obviously, well, given that QCD is around roughly 50 years by now, and we're still talking here about QCD strings, obviously, understanding what QCD strings are is quite a hard question. And, well, questions can be hard for various reasons. They can be hard because they're just hard, and also we don't quite understand what makes them hard. And also, they can be hard because they're not sufficiently well posed. So I think this starting point will help us to first also kind of to focus on the correct versions of the question what QCD strings are, which will be well posed, sharply posed, so at least we know that there should be an answer. And also, hopefully by the end of this lecture, I will also explain to you the reason why this question is hard. Okay, so let me be a little bit more specific. So to start addressing this question, let me be a little bit more specific what I mean when I say that theory exhibits like contains string-like objects. And, well, again, over the course of these lectures, we'll discuss several definitions for that. And here I'll start with kind of most simple-minded, which comes like again from thinking about it as a Lorentz effective field theorist. It's basically the statement that the theory has a subsector where the full, I should say, I always think about relativistic theories in this lecture. So the full theory is invariant under d-dimensional Poincare group, and so the presence of a string, of a long string, that's a statement that there is a subsector where the full d-dimensional Poincare group is broken spontaneously towards the product of two-dimensional Poincare along the wall sheet and rotations, transverse rotations, which are
Why spontaneous?
yes. So there is a just by the presence of a string. So that's yeah. Sorry.
Explicitly broken.
No, it's
So why spontaneous?
well, it's broken by there is a sector in the theory by which I mean you put a string.
The state, choice of the state.
Yeah, by choice. It's in the same way how I break spontaneously by my presence here Poincare symmetry. Infinitely the long string spontaneously breaks the Poincare symmetry in the theory like that. So that's kind of that's effective field theorist way of saying that theory has long strings. Well, strictly speaking, well, it's maybe not quite kosher to call this subsector because it has infinite energy, because the string is infinitely long. So you may think of doing something like the following. So you may put your theory on a circle and wrap around the string around the circle, and then consider the limit when r going to infinity. We'll do that later because that literally corresponds actually to what people do when they study strings on the lattice. But for now, let's now already work in this r to infinity limit. And also, well, also let me make another assumption which is not necessary, but it will apply in the cases where I'm mostly interested in particular, well, in those which I mentioned. Let's assume that in the absence of the string, this area has a gap. So there is lightest particle, which in case of pure glue, that's the mass of the lightest glue. Then, in the presence of the string, from the fact that the string spontaneously breaks Poincare symmetry, in particular, it spontaneously breaks translations. We know that there will be d minus 2 Kepler's excitations, d minus 2 massless modes, which correspond just to translations of a string. Right? So it's xi, so where I for me runs from 2 to d. I'm imagining that the string, like unperturbed string, is stretched in the first direction. Okay.
Sorry, why are we considering an infinitely long string in the first place?
Well, that's.
In QCD, I wouldn't expect the string to be infinitely long, right?
Sorry, what?
In QCD, I would not expect the string to be infinitely long.
Well, in pure glue, it can be as long, infinitely long. So I talked about pure glue, and then if you by QCD you think about theory with fundamental forks, yeah, then kind of that's next question, well, how to describe breaking of a string. But that's but there are several answers to that. Again, I think from effective field series perspective, because that's the cleanest way to pose the question. But also, I think in general, so if somehow we want to understand dynamics of a string, it makes sense to consider it in a kind of most symmetric and simple state. So,
in pure glue theory, you would take a closed string and not an open one, right? It's closed.
well, it's again, you may think about closed string wound around closed compact circle, but in the limit when you take the size of the circle to infinity, it doesn't really matter whether it's closed or open. Also, you may think about string like that, which is stretched between a pair of quark and anti-quark. By the it will be common very soon. Now, okay. So again, if you are effective field theorist, so the moment you have this setup, you know what to do. There is a developed machinery how to build low energy action, which describes dynamics of these massless modes. In this case, it reduces to very simple prescription. So the way to build low-energy effective field theory is that you introduce object which you call x mu, which is a vector of this kind, and you should think about it kind of the system of goldstone bosons, which effective field theorists are most used to pions. So that should be sort of analog of the U field for pions, and then the most general. Then you write the most general action constructed of the local invariance of the embedding of the string voltsheet. sheet. So of course this x mu, they just define embedding of a string voltsheet sheet into the target space, and so you write the most general action, which some of the local terms described in this embedding. So in particular, well, you define the induced metric, which is delta x mu, and then you write the term sigma minus that's the leading term, that's Nambu-Gold action, the area, and then you start writing terms, for instance, like plus alpha r plus beta r squared, where r is the intrinsic curvature on the world sheet. But in addition, given this geometrical data, you can also define extrinsic geometric invariance, and there is extrinsic curvature. And so in this action, you also allowed to write terms like plus etc. So, well, that's again, if you are effective field theorist, that's your approach to the problem, and the cutoff of this theory is given by the lightest massive particle present. So it's either the global, which is present in the theory. Well, in principle, there could be also massive excitations on the string itself. So, there is a dimensionful parameter here, which in case of QCD string, that's what determines the tension of a string. And so, for instance, in QCD string, the global mass is for the string tension for the lambda QCD, and also one expects if there are any additional massive states localized on the string, one expects them to have the same mass. Okay, in principle, then you know what to do. You can start calculating various physical observables in this effective field theory. Yes?
Why don't you write the trace of k? It has less derivatives there and it's a scalar of all the terms you give.
No, but that's, well, first of all, it's not rotationally invariant, right? Because yeah. I guess in 3D you could have written it as a break parameter. But also it's total derivative. Okay, well, note by the way that I'm doing something slightly unusual here because I'm discussing with you theory of goldstone bosons in 2 dimensions, right? Bullshit is 2-dimensional, and I'm discussing theory of goldstone bosons. Well, there is nothing wrong with that. This is a counterexample to Coleman, Merman, Wagner. This is a theory of interacting, like honest-to-God goldstone bosons in 2 dimensions. There is nothing wrong with Coleman's paper, apart from the title. So, because what the paper is called, there are no goldstone bosons in 2 dimensions. That's wrong. What's correct is there is no other parameter in 2 dimensions. So basically, the statement that basically what is proven there that the massless scalar field is not a good operator in 2 dimensions in massless theory.
Didn't it also have to decouple from everything?
Well, there are, indeed, there were counterexamples before, like other counterexamples which involve some Lagrangian theories where one gets goldstone bosons which decouple from everything. This counterexample is more interesting because here there is no. These are really interacting goldstone bosons whose with non-trivial scattering amplitudes, as we'll discuss now, whose interactions are controlled by nonlinearized symmetry. So in that sense, it's really physically sensible counterexample. Again, the way it gets around the Coleman argument is that, well, operator X, as we'll see, it's not well defined. There is no such operator, but it never appears in this action. So X is always entered with derivatives. But there are massless excitations in this area. So like if you imagine you have this long string in this room, then there are massless excitations corresponding to wiggles on the string, and then they interact with each other. So with the strengths set by the string tension.
This Riemann scalar is calculated with respect to the inducement.
Sorry?
This Riemann R square calculated for G alpha.
Yeah, that's all calculated using this induced method. Right. So,
this is the effective action of the massless mode, so the string itself is the same thing.
Well, this is the effective action describing gatless excitations which are present in this sector in this area where we have infinitely long string. Well, and of course, assumption here that there are no additional massless fields, which would be correct if there is no reason for them to appear. So, for instance, I could have considered, maybe I commented on that before, one could consider, say, different coset. I may consider some supersymmetric coset, and that will be extra harmonic degrees of freedom. But examples I mentioned, like a billion Higgs model or pure glue, there is nothing like that, so we don't expect any additional massless degrees of freedom, and indeed there are none. So yeah, that's effective Lagrangian describing gapless excitation in the sector which we want to study. Okay, so let's start calculating some simplest observables, which one can calculate. And well, I already kind of said that. Again, if you are particle theorist at least, and then when you have an action, the most natural observable for you to study is start calculating scattering amplitudes, right? So, yes.
Is it a critical string?
No, that's my starting question. So that I want to see when will it matter that the string is non-critical. So far I'm just doing effective field theory, and what I want to see when I will hit the point that d equal 26. I will see that d equal 26 is special. So far, none what I said so far it's it can be said in any number of dimensions.
It's an assumption that we have massless excitation.
Well, it's a starting assumption that I started with a theory which have a string, like a billion Higgs model in 4 dimensions, or pure glue. So I have a string-like object, meaning that there is a spontaneous breaking of Poincare with this symmetry breaking pattern, and then I guarantee to have massless excitation in that sector, which just corresponds to translational modes of the string. Yeah.
I don't fully understand. This should be the action of the xi?
Yeah, this is the action of describing dynamics of xi's. Yes.
So why is the integral over b to sigma and not over mole dimension? Don't you work?
Huh?
So this is the working action.
Yeah, that's a bullshit. Yeah, because in this sector, the massless degrees of freedom, they're even bullshit. Yeah. These xi's, these are the xi's. Their fields. They depend on two-dimensional coordinates.
Will you impose conformality of the theory?
No, we don't impose conformality, but more or less, theory is manifestly non-conformal. It has dimension full scale. There is a tension of a string. All what we're imposing the just target space symmetries, right? So we're imposing.
And is this a quantum theory or a classical? At this point?
Well, at this point, it's effective, long effective field theory. So, yeah, we'll start calculating quantum amplitudes using it, right? But it's not. Well, it's not UV complete. So, I mean, as I said, there is a cutoff set by the scale, and we're studying long dynamics. Right?
So if you did study string theory, you know that there will be an anomaly in the theory will not be Lorentz invariance, so all the initial ingredients are wrong. Are you trying to find a different thing that will be a problem?
No, yeah, that's kind of was the initial question, because clearly what you just said cannot be the case, because we know pure glue is there, we know a billion Higgs model is
nature.
Yeah, but we know that theories are there, and kind of they have strings, and those strings are guaranteed to be described by this kind of Lorentz action. And we know that nothing wrong goes with Lorentz invariance. So indeed, when you open some string theory textbooks, they will say that there's some problem with Lorentz invariance, containing strings away from d equal 26. That cannot be true, right? Clearly, we can QCD is well-defined theory, and we can study the strings on a lattice, and people do study them on a lattice. And so it is a Lorentz invariance theory of strings in 4 dimensions. So it's not Lorentz invariance. So basically, yeah. So sometimes I can kind of, I think, now pretending that I know a little bit of string theory. Sometimes you may there is somehow there is a conflict between people formulate the default 26 anomaly conflict between Lorentz invariance and conformal symmetry. But again, because conformal symmetry is a remnant of the reparameterization invariance of the bullshit. It's a gauge symmetry. So the only physical symmetry present is Lorentz invariance. So the conflict should be between Lorentz invariance and something else which is physical. So as you saw in this language, I never, well, that was on purpose, but I never introduced reparameterization invariance, and I never introduced conformal symmetry. Of course, in other language, I just fix the gauge, right? I fix the gauge x0 equal to tau and x1 equal to sigma.
So in your discussion, the notion of reparameterization in the logic is not there because you already fixed something, and you expect that you will be consistent because models can describe those things in nature.
Right.
And yet you expect problem, and you're going to find something you're going to tell us what it is. I just try to orient myself.
Yes, that's the logic. Yes, right, exactly. I want to see what the problem in this language is equal to success.
Why find the gap the global mass?
Sorry?
You find the gap of the theory the global mass?
Well, that's a gap in the absence of a string. In the absence of a string, that's the lightest particle present in pure glue context. That's the global, right?
So, the global, so can I think of the global excitation of the launch? How?
Well, in the language, I will be using global corresponding. That's excitation, like in this list of with my plan. Global is excitation of it's a short string, which kind of in this language it corresponds. They are closed strings with zero winding. That's what globals are. And what I call long string, that's I can see the string with I can see the winding sector, and I take the circle radius to infinity. So, are there any more questions about setting? Yes.
So, we take the fixed figure, we take the low energies like in space-time, but then we thought about also as the low energy effective theory in the logic. So, how do you relate these two?
Well, I started with quantum field theory, so there is, well, it's just, well, when I talk about low energies, here I mean low energies energies above so the string itself carries infinite energy or very large energy in the limit are going to infinity. So when I talk about low energies, I mean excitations above that ground state. But it's always measured by target space clocks. So it's I'm talking about non-gravitational theory. It's like QCD, so there is no subtlety in defining what energies are. Okay, so if I'm particle series, I said the simplest thing for me to calculate is to start calculating scattering amplitudes of these guys. So one may be worried here, and at least when I started doing this, I had prejudices that somehow, coming from the same Coleman's paper, that there is something wrong about calculating scattering of massless bosons in 2 dimensions. So I expected that if it starts calculating these amplitudes, that there will be some IR divergences. But then you start calculating them, and you find that there is none, and the amplitudes are well IR behaved. And well, at the most basic level, it comes about in the action which I just erased. There is derivative sitting on every x field which appears there, and that's enough to tame all the IR divergences. But more kind of invariant argument is the following. So the IR divergences in general, kind of the fact that massless S matrices are badly defined, especially in 2 dimensions, they have to do with the fact that, well, when you have, say, either one right mover, massless right mover, or a bunch of massless right movers, then because, well, in 2 dimensions there is only one spatial dimension, so all particles, they move in the same direction and they move with the same, if they're massless, they move with the same velocity. So even asymptotic past, asymptotic future, they don't separate from each other. So that may cause problems in defining scattering and defining S matrix. But the point is that the structure of the theory, which we just wrote here and erased, that this is a free CFT deformed by a bunch of irrelevant operators.
You restrict yourself to Nambu-Goto now, or
Huh?
you restrict to Nambu-Goto?
No, not well. I can talk about all of them, right? But starting from Nambu-Goto, so Nambu-Goto, it has there is free kinetic term, and then when you expand it, then there are, roughly speaking, x to the 4 interactions plus etc. And these other operators which I wrote here, they just introduce more terms like that with more derivatives. So what we have a bunch of free massless bosons which interact through irrelevant operators. And then if I have only right moving particles like that, then, well, S matrix is Lorentz invariant, so I can apply a boost to them and I can make them arbitrarily soft. And when I make them arbitrarily soft, the interactions disappear, they turn into free particles. Well, it's just a complicated way to say that if I have only right movers, they don't interact in such a situation. So that even though formally it's true, they cannot be separated from each other, but it doesn't cause any problem in defining corresponding amplitudes because they're already free in the absence of left movers. That's the reason why the corresponding amplitudes are well defined and one doesn't find any higher divergences there. Okay, so let's discuss what do we expect from these amplitudes and before actually calculating them. And I said this is a system of goldstone bosons, so let's phrase our expectations in terms of current algebra for corresponding nonlinearized symmetries. So first of all, there is a shift current, which is associated with symmetry, just a shift symmetry. Right, so I can shift all axes by a constant. And this shift current, corresponding shift current, it has the following structure. The alpha xi, that comes from just free kinetic term, plus some addition, which is, this addition is nonlinear in excess. And then, as usual in derivation of soft theorems, I can consider 0, which is a matrix element of the divergence of this current between some in and out states, and then I can write this as a sum of these terms. So there is and then when I take an p squared equal to 0 limit, then this term here I have a z pole, so this will turn into state with additional particle, and on the right hand side, because this operator is nonlinear in excess, there are no z poles here, so well, I get, it is what it is. I get this matrix element. And now if one takes soft limit, so after going on shell, if I now take p to 0, one doesn't expect any poles in the right hand side because this is nonlinear current, and this is kind of that was the standard argument which derives that goldstone bosons, the amplitudes are soft. Of course, in this case, in the case of this area, I didn't have to go through all this derivation because unlike for pions, which appear in the action without derivatives. So here this fact is completely obvious to start with, right? Because X field appears everywhere in the Lagrangian, it appears with derivatives sitting on it. So if I calculate an on-shell amplitude, some computated on-shell amplitudes, they all will be manifestly solved. So that's completely obvious here. But there is also, but we have more than that. We also have non-linearized boosts and non-linearized rotations. And so we can run similar argument for them, namely the corresponding currents. So the fact that this area has non-linearized boost, well, here this is a current which corresponds to boost or rotation between transverse direction labeled by I and Walsh direction labeled by beta, and the corresponding current, it has schematical form is the following. So there is a part which is proportional to the shift current. So it's just a statement that boost or rotation is the same as the shift, which is linearly modulated, plus there is addition, which determines how field transform under these transformations, which is sigma independent. And for instance, starting with Nambu-Gotha, one can work out explicitly. So this k term, it starts with beta xi plus xi t alpha beta plus etc. So where t alpha beta is the energy momentum tensor of d minus 2 free bosons, but that's true in general. And now the conservation of this current, the statement that this current conserved, implies that the shift current itself is a derivative of this k term. Just because when I take it divergence and the derivative hits the shift current, I get 0 because it's conserved and so on. So I'll get only term from derivative hitting the coordinate, and I get this relation.
Sorry, in this middle one, so p squared equals 0, so the first term is 0?
Here, no. I take the limit p squared equal to 0, and here the first term became the on-shell amplitude, because there is a lazy pole in this term, right? Yes. So it's not 0, but rather there is an on-shell pole. But now we got extra piece of information that the shift current itself is a derivative. And if I separate, so let me call, let's say in this k term, let me separate the leading order term. That's in what's written here. That was this xi. That's what appeared on the left hand side. Let me call this addition here. Let me call it k alpha beta I. And so this. When I plug that fact, so that's additional fact which follows from the fact that it's not just a system of translational goldstones, but a system of goldstones which realize also rotations and boosts, then I have the following statement. In other words, this argument indicates that amplitude should be not just solved, but it should be doubly solved. So when momentum of angular particle goes to 0, they should vanish as the square of the momentum. Well, which makes sense intuitively, because softness of the goldstone bosons is kind of usually explained by saying, well, if you kind of shift your vacuum by constant, then the theory doesn't change. But if you modulate, like locally modulate the vacuum expectation value, then in the limit when the gradient goes which determines the rate of the modulation, when the gradient goes to 0, there is no physical change, and that's manifest in the softness of the amplitudes. And here, but this, in addition, in addition to constant shifts, theory is also invariant under kind of linear shifts, because it's invariant under rotation and boost. So it makes sense that we got this result. That was expected. However, one might be somewhat worried here, because even though for calculating the amplitudes, as I said, I don't really need to use operator x. I can always use derivative x. In this argument, x does appear here, so explicitly. So one might worry that there is some subtlety with this argument in two dimensions. And so let's, well, whenever you have a general argument and you're worried that maybe it goes too quick, it makes sense to try to calculate and see what happens. So we have the action, and we have, we're doing effective field theory, so we're expanding amplitudes at low energies. So at low energies, all the leading amplitudes, they just follow from Nabu-Gote action. So we can calculate straightforwardly. I wrote, so Nabu-Gote piece of the action. Xi squared plus schematically xi to the 4. There are different contractions here, the xi to the 6. Again, there are different tensor contractions. So you can just start calculating these amplitudes. But you find the following. So at 3 level, there is no big surprise. There are well-defined amplitudes, as I said. But if you are patient enough to calculate, say, not just 2 to 2, but also 2 to 4 or 2 to 6 scattering, then you find that all those amplitudes vanish. So there is, so in other words, at the level of 3 level scattering, Nabu-Gote theory is integrable. Well, actually, also at the level of 2 to 2 scattering, it's not only integrable, but it's particularly simple. So the amplitude which you find is this form. So that's 2 to 2 amplitude, which corresponds, I'm scattering to I, J, K, L. That's kind of the flavors of initial scattering particles. And at 3 level, when you do this calculation, you find that the scattering is purely diagonal. So all what happens, particles just go through each other without changing favor. So in other words, for instance, if initially I started with a string kind of oscillating in this plane, as a result of 3 level scattering, it stays oscillating in that plane. It doesn't get excited in the transverse direction. So that's a 3 level 2 to 2 amplitude. And as I said, for multi-particle amplitude, they're all just products of this, and there is no particle projection. That's a 3 level story. But let's keep going and proceed to 1 loop, because at the end of the day, well, the subtlety, we expected that 3 level is kind of, it's almost like doing classical physics. It's not exactly like that, but it's almost doing classical physics. So one expect that d equal 26 appears at the loop level. So let's do one more step and calculate 1 loop amplitudes. And here, actually, already something interesting happens. Because normally, calculating one loop amplitudes in a series of goldstone bosons wouldn't be too instructive for the following reason. So if you have, for instance, a series of pions, then there is a leading order term in the Lagrangian, which is analog of Nambu-Gote term, and all three-level amplitudes. Leading in the derivative expansion, all leading amplitudes are determined by this term. But the moment one starts calculating one loop amplitudes involving this term in the action, so here I'm talking about four-dimensional theory, then at the same order in derivative expansion, one starts getting contributions from operators like this. So in other words, so one loop here is the same as the same order in the expansion in energies as three-level coming from here. So in other words, the three-level amplitudes in a series of goldstones, they're completely universal. They're just fixed by the leading order term. But when you go to one loop order, typically you start getting non-universal contributions due to higher order counter terms, which you can write in your effective action. So here, where Nambu-Gote is special, namely at the next order in derivative expansion, again in the line which I erased here, there were three operators. There was this square root of R, then there was k alpha beta squared and k alpha alpha squared. Now, of course, this one is a total derivative. Yes.
Can you remind what is U?
Well, U is a fine field. I'm just making so U.
It's a comment.
I'm making an analogy with it. Okay, so as I said before, so kind of in this construction of flow injection, X mu should be thought of as an analog of U field in the fine sigma model. Yes.
What you said about the three level there, is it universal or universal?
Huh?
What you said about the three levels, is it universal or universal?
Well, it's the same because it's fixed by Nambu-Gote part. All other terms they will contribute high. They will be high order because they involve more derivatives. They will have so at the low energy limit. That's the leading universal part, which is determined by Nambu-Gote action. And so now I want to calculate one loop contribution from Nambu-Gote action. And what I'm saying is that a priori one would be worried that at the same order one starts getting new parameters. There are new contributions coming from associated with now operators like this. But the point is that this one is total derivative. Then there is a relation between these three guys due to Gauss-Kadazi. And this guy, so that means I can reduce everything just to this operator. And this operator, well, it's just, for what reason here, it's the same as this. And that vanishes on shell because box x equal to 0. That's Nambu-Gote. That's the equation of motion following from Nambu-Gote. Which means, well, that these operators actually, well, that this operator is redundant. It can be removed by field redefinition. So, in other words, just it doesn't contribute to on-shell amplitudes. So
that's true only if you don't have singularities. If you don't have curvature, like if you have folds, then at the curvature of singularities, you cannot ignore this.
No, here I'm talking about scattering for long string, right? So by definition, I'm doing low energy expansion. So
you assume that there are no folds here.
Well, I consider long string and study the dynamics of low energy excitation. So that's kind of assume that there are studies excitations without folds. Right?
And this equation of motion simplification is only for k alpha alpha square. Is it also true for k alpha beta beta?
No, so what's true is that the equation of motion is this.
Yes.
Yeah, so it's that vanishing of k alpha alpha. That's the same as
Oh, I see that.
these vanish, but then k alpha beta can be removed, expressed through r and k alpha alpha squared.
Oh, I see. It can be
But
expressed.
we are Gauss-Kadazi,
Oh,
and,
I see.
and r is a total derivative. So basically, at the end of the day, you can write all these operators, but then you will calculate three-level amplitudes coming associated with them, and you find that they all vanish. So this is just explanation for why that happens. So that means that in this series of goldstone bosons, also not only three-level amplitudes, but one-loop amplitudes are universal, since they completely fixed by leading order term in the classical action. And so it makes sense to go ahead and calculate them. And so when you do that, so at the level of 2-to-2 scattering, you get. So first of all, there is a correction to transmission amplitude, which is just fixed essentially by unitarity. 16, something good. GL. But in addition, one gets a annihilation amplitude. So the scattering is no longer diagonal. The 2-to-2 level. So the scattering amplitude like that. Cube delta. Okay, and we kind of start seeing what we wanted. The coefficient in front of this amplitude is d minus 26 over 192 pi. And moreover, so you see that some property of the three-level theory, which kind of what I said, this amplitude just says that scattering is non-diagonal, that if you, as I said, if you start with a string which oscillates in one direction, it keeps oscillating in that direction, three-level interactions, but due to one-loop effects, it's now gets excited in the transverse direction. But one can also calculate 2-to-4 scattering, and one finds that it's non-vanishing. So there is non-vanishing 2-to-4 amplitude, which is again proportional to d minus 26. I'm not.
Where is this factor of d minus 26 comes from?
Well, it comes from just calculating.
No, but there must be some reason to that. It's not related in any way to goals or stuff like that. It's just a matter of the calculation.
Well, it's a universal number which comes out from calculating these amplitudes. As I said, I'm doing here something very bottom up. So yeah, no, I'm not sure what kind of answer.
Have you done a similar calculation with fermions instead of this number what option for scale for this? Would it be?
Oh, very good. So, but okay, let me first formulate the. So I think we got to the point when we obtained the answer to the question which I posed at the very beginning, right? Namely, what's special about like what one finds is that Nambu-Goto theory is integrable at the tree level, at the classical order. But if you are in non-critical dimension, that there is no, and here I'm talking really about quantization of long string. So there is no way to quantize this theory consistent with Poincare invariance of underlying quantum field theory and preserving this integrability. So there is universal particle production which appears with one loop order, and there is nothing you can do to cancel it. So, kind of at least from the point of view of this sector, the conflict is between Poincare invariance and classical integrability present in this theory. Now, yeah, indeed, for instance, one may to test how universal this is, one may look at superstrings, what happens with fermions. And I was always puzzled by the following statement.
26-dimensional Poincare invariance?
Huh?
You're talking about Poincare invariance in 26 dimensions? Where do you see the conflict of Poincare?
Because if D is not equal to 26, then there is particle production. So you can quantize this theory as Poincare invariant Lorentz effective theory, but there is but classical integrability is necessarily broken.
Yeah, but why is it in conflict with Poincare invariance?
Good. Because if you see this term in the amplitude, well, which I wrote, and actually all these other terms which I wrote there, they are even though they come from one loop calculation, they are polynomial. They correspond to so-called rational terms. Which means if I didn't worry about Poincare invariance, if I just was worried about translational invariance, shift symmetry, then I could have cancelled this particle production, roughly speaking, by adding a term like schematically like this, like alpha beta squared. So there are terms with this structure, which I can write to this series of goldstone bosons, which would allow me to cancel this particle production. And the problem with these terms is that they are not compatible with, well, they don't come from local geometric invariance. They are not compatible with non-linear realized Poincare symmetry. So if I just look at this series, a series of massless bosons in two dimensions, and insist only on translational symmetry acting on X, then I can build an integrable model by canceling this particle production. However, what prevents me from doing that, it's extra requirement that there is no linearized target space Poincare symmetry.
Any action you write in terms of X size can be rewritten in a 26-dimensional, in Poincare invariant way, because it's in a fixed gauge. But it probably would be having a low. No. For instance, already at Nambugota level, right? At Nambugota level, for instance, here there are two terms. Like if I talk about dx to the 4, right? So there is a term like this, and then there are terms like d alpha xi squared, the whole thing squared, and then there is a term d alpha d beta xi. D alpha, d alpha xj, d alpha xj, d alpha xj, d beta xi, d alpha xi, d beta xj. So from expanding the Nambugota square root, there will be these two terms with very specific values of the coefficient, and non-linearized Poincare symmetry tells us that these coefficients should take these values. So I cannot change ratio between these coefficients. The moment I change ratio between these two coefficients, it's still a series of goldstone bosons, but the goldstone bosons just of translational symmetry and not the non-linearized boost interpretation.
Would this be sick if you add these additional terms where the number of x's and x's are not the same? And as you said, you can cancel this term then.
Well, it's not sick as a two-dimensional theory, but it doesn't describe relativistic string. It doesn't really describe string coming from relativistic target space theory with Poincare symmetry in the target space.
Does it mean that you can write a long string in any dimension with no critical dimension? Okay, which is not fully Poincare invariant.
Yeah, for instance, if you talk about if you are talking about like vortices in superconductor, right, where there is a medium, then in general you may have these coefficients, may take them different values. But here we're talking about strings in the Poincare invariant theory, so these coefficients are fixed, and that's what fixes tree-level amplitudes. That's what makes this integrability at tree-level universal, so it enforced by.
But let's say in the same line, so let's sacrifice classical integrability. Okay, are we punished in any way for that?
Oh no.
So that can be done in any dimension.
That's kind of the answer. At least from this viewpoint, what's special about critical dimension is that in that dimension, this long string can be quantized, preserving integrability. but if d is not equal to 26, well, actually, well, it's something which is not seen from here, but one can check. Also, like d equals 26 is special. Also, d equals 3 is special. We'll come back later to that. But basically, well, for instance, at the level of this amplitude, because there are some kinematical cancellations. If all flavors are the same, that Q1 gets S cube plus T cube plus U cube, which vanishes. And the same happens for all other amplitudes. So strictly speaking, at the level of this analysis, the statement that theory can be quantized, consistent with Poincare invariance and integrability at d equals 26 and d equals 3, but not, for instance, at d equals 4. Okay, so...
But again, why do I care about the classical integrability? It's
No.
not the holy principles.
No, it's not the holy principles, but yeah, well, but we got the answer to the question we're asking, right? So we wanted to see when you will... But
Can you relate the integrability to the way d equal to 26 appears in the metric string description?
well, I think from this perspective, what's special about critical strings is not that they're consistent, but that they're simple. So quantization of critical dimension is simple because you can quantize this theory by imposing integrability. And actually, well, I promised you to say that we'll get the answer why the question of understanding QCD strings is so hard. I think we got the answer. So if you take pure glue, so I think the dream was something like that. You take pure glue, you take 12th limit, then scattering between glue balls becomes free, meaning that there is no string breaking, and somehow one will be able to solve that theory. So what we see that will never happen, because even in a strict planar limit, if you look at the long string, the dynamics of the long string is intrinsically non-integrable. So there will never be such a thing as really solving pure glue theory in the strict planar limit, as it was kind of achieved for n equals 4 superior meals. So analog of these calculations for n equals 4 superior meals. Of course, there are no confining strings there, but there is a statement that bullshit S matrix is integrable for strings in the ADS for 5 crosses 5. And here bullshit dynamics is not
So the
integrable.
status says, as you see it, if I understand, you can do this effective theory as a consistent theory in any capital D. You cannot say much if D is not 26 or 3, because D is 26. But thermopathologies are no problem. But obviously, unless D equal to 26, you cannot describe it as an embedding of a reparameterization environment worldsheet in target space and so on. This we know that you cannot do consistently. But
Well, I'm not sure what that means, because
because here in the language of embedding reparameterization invariant worldsheet target space, this is choosing a particular gauge, and if I would choose a different gauge, you will get a different theory.
Yeah, no, it will be the same theory. No, there is no normally you can there is no problem with reparameterizations. You can write Nambu-Goto. Yeah, what I did here, I fixed the gauge x equal tau, x1 is equal sigma, starting from Nambu-Goto description. I can introduce back that reparameterization invariance, and there is no problem with that.
No, the problem will be that it will be anomalous.
No. That's not what anomalous is a Polakov description of this theory. It's not a reparameterization. If you want to rewrite the theory using Polakov method,
I see.
that's what becomes anomalous.
So you say Polyakov and the Nambu-Goto equivalent quantum mechanically if and only if D is equal to 26.
Right.
The Nambu-Goto, you don't know to solve it for any D, only for D equal to 26, but otherwise it's okay. That's the statement?
Yes, that's the statement. Oh, yes.
So you mentioned n equals 4 superior mills. Can you see the integrability in your language there, or?
Well, there it's a little bit more subtle because there is no really confining flux tubes. One needs to talk about strings in ADS 5 crosses 5.
Okay. So
But the bullshit. But that's the usual integrability, and actually, well, the S matrix which one gets here in the critical case, it can be obtained at flat space limit of dressing factor, what was called from EDS 5 process 5. So that case is just a little bit more subtle because it is no really confining flux tube. But the
But
worksheet.
it's still strange, because
Yeah.
Nabucco and Polyakov are equivalent classical. Yet quantum mechanically they are not. You can quantize this one, but not this one.
Right, and actually, well, I'll show you how to derive this. Yeah, how to derive the same amplitudes. Actually, I didn't write this expression for you for 2 to 4 amplitudes, but Polyakov-like description actually provides a single expression for all 2 to n amplitudes at one loop.
So they all have a D minus 26?
They all have D minus 26, and there is kind of simple generating functional for this all these one loop amplitudes, which can be written kind of thinking about how to formulate the theory in Polyakov.
Polyakov, I mean, something must happen. I
Huh?
mean, dilaton should be turned on. It can't be that they're not equivalent, right? At the end of the day.
No, but again, we know experimentally that QCD strings exist, and they don't have any like dilaton-like degree of freedom there.
But maybe they're secretly there is an internal space that we don't see that make the theory consistent. I don't know. I mean,
Well, we'll discuss it, but there is an experimental fact, again, which follows from just lattice simulations, but also it will be very surprising if that was not the case, that if you take long string, there are no extra massless degrees of freedom there. And that's all what is needed for this argument. There.
And higher loops also?
Okay, we'll get there, but maybe before going to higher loop, just as an additional data point, let me get back to Kobe's question about fermions. For instance, I was always puzzled by the following statement in many string theory textbooks. They would say well, for bosonic strings, look, it's interesting, theory consistent classically in any number of dimensions, but then the quantum mechanically it only makes sense at d equal 26. Yeah, for superstrings in Green-Schwarz formalism, already there, even classically, there is this special number 3, 4, 6, 8, 10, if I remember right, when one can write kappa invariant Green-Schwarz action. So they're already classically.
no way.
Sorry, no way. I told you I don't know string theory. The statement is somehow already classically. There is consistency requires that select these special dimensions, and quantum mechanically d equal 10 again selected. Again, if you are effective field theorist, that doesn't make much sense to you because you can proceed in the same way, right? So you can write super coset, and you can write, okay, there will be extra fermions, extra bosons, but you will be able to write theory like that with extra fermions, which would realize like corresponding super coset for long strings in any number of dimensions. So what happens is the following then. It turns out that for these supersymmetric cosets, basically there is an amplitude like with 4 fermion and 1 boson, so 5 particle amplitude, which already at 3 level is non-zero if you're not in these dimensions. So at least this language about integrability at least allows, in both these cases, it tells what's going on. So for superstrings, for supercosets, at the classical level, there, again, the statement, what's special about these dimensions in this kind of invariant, well, at least in the long sector, invariant language, by invariant I mean based on some physical observable scattering amplitudes, is that it's only in this these dimensions, theory is integrable at the classical level. But then again, one calculates one loop, and one finds that, well, it's either d equal 10 or d equals 3, also special, this anomaly. For the same reason, it vanishes at d equals 3. So at least this cross-check, this strategy passes. So it also explains answers to effective field theorists. What's special about these dimensions for superstrings?
Getting integrability and absence of anomaly, are these somehow related?
Well, at least in the language which I'm using, the anomaly is the conflict between integrability and Poincare symmetry, which are both present at the classical level. So if you start with So that's really what you cannot achieve in non-critical dimensions. So without changing the, well, anomaly in gauge theory, in gauge symmetry really means whenever gauge symmetry is broken, that means you need to add extra massless degrees of freedom. So here we start, maybe kind of that language will help, right? So here we, from the get-go, we said that we're not going, for long string, we're not going to add any extra massless degrees of freedom on the whole sheet. So that's kind of equivalent saying that gauge symmetry is there, right? And then the conflict, the moment you fix that, then the conflict is between classical integrability and Poincare symmetry. And then you, looking at this as a two-dimensional theory, you have choice. You may either insist on integrability and make quantize the theory with an integrable theory, or you may, well, if you care about QCD strings, for instance, you have to keep Poincare symmetry, and then you lose integrability.
Sorry, but Sergei, I mean, so you've seen it from this Walsh scattering application, but is there a trace of it also in the spectrum? So suppose that you want to solve the spectrum, two-dimensional spectrum of this series. Would you see any problem if you're not at G = 6?
Well, presumably, and that becomes much harder. So as I said in the beginning, kind of, I wanted to see, well, applying this later to QCD strings, I wanted to see why the problem is hard. Well, we see why it's hard, because we need to deal with intrinsically non-integrable systems. There is no hope that we'll actually exactly solve it. But also I wanted to have something which is well posed. So here I understand, like for long string, at least I have well-defined set of observables, bullshit test matrix. I don't have kind of, without thinking, and effective field theory is all about to avoid thinking, right? So there are a set of rules, you calculate things, if you understand everything, you get the right result. But to do something like you're suggesting, to calculate the spectrum of hadrons, I don't know what question to ask to this two-dimensional theory. So that requires thinking, that requires extra physical input. But the expectation, which kind of we see in the spectrum, is that for critical strings, when you look level by level, then there is exact degeneracy on each level between string states. And one expects that degeneracy will, well, it's probably related to some integrability, which is present in the theory, and that degeneracy will be broken, and that's the case. Yes?
We actually have a very strong conjecture. You say there is a consistent string theory or superstring theory. I don't know, I want to ask about the tachyon, but so let's suppose it's a superstring on time times a circle times d minus 2 dimensional internal space. Perhaps the Virasolo constraint would be similar, d equal to 26, but L0 would be some A that depends on d minus 2. It will not be 1, it would be probably d minus 2 over 24. And you claim that there is a consistent string theory like that?
No, I'm not, because in the last part of your statement, you make an assumption there is some Polakov-like description with local bullshit CFT. And already, like for usual strings, for fundamental strings, for Ramon backgrounds, we don't have that, right? So.
No, I mean, if d is not equal to 26, I don't know how to quantize consistently for your code.
Right, but I'm not making a conjecture.
I don't make this conjecture. I said that you make this conjecture.
No, in formulating what was my conjecture, you put in that there is a Polakov description.
No.
Well, but
all I said is
yes.
that you claim there is a consistent, let's say, superstring, not necessarily in 10 dimension, in time, times a circle with radius r, times d minus 2 dimensional space.
Well, that's not my claim.
The rest was my guess of what would be the.
Yes. So the first part.
You claim that there is such a.
Yeah,
that was my guess of what would be its properties. That's right.
Right. So yeah, the first part of the claim is a fact which we know just from existence of QCD. Like if you take pure glue theory and put it on a circle.
So what is your claim about the conjecture that there is a consistent string theory?
Right.
Whose properties are?
Well, that it exists in 4 or 3 dimensions, for instance.
No, but what can you say about its properties? Is it tachyon there?
No, there's no tachyon because QCD doesn't have tachyon, right?
No, but your model. What are the properties of your model.
But that's the whole point of this lecture.
Oh, you will continue.
But yeah, that's what we're trying to understand. We know there is experimental fact that such a theory exists, and we're trying to understand it, right?
Is it consistent to concrete with a two-dimensional theory of a long string? That shouldn't it, when you scatter excitations which live on the string, will it emit something into the bulk?
Very good, very good. That's was number 2 of what I'm saying. But how I'm doing on time? And I wanted to do something else, but that's one of the most important questions.
So can you repeat it?
And it is. So let me. So what Nikita is asking is that if I take, and so really, I think I promised you that eventually I will formulate kind of at least simplified but sharp version of the question what QCD string is, right? So my favorite version of this question is the following. So indeed, as Nikita says, if we take a long string in QCD, right, and we start scattering, then when we go when the excitation energy becomes larger than the mass of the lightest glue ball, then string will self-intersect, and kind of you create this, and then you emit closed string. So really, there is the QCD string that exists only as low-energy effective field theory object, and it's with a cutoff of mg. And that's true, by the way, that's true for n equals 3, that's true for abelian Higgs model. But what makes QCD strings interesting, what makes them really interesting, that we have another parameter, right? We have parameter in C. So what we can do, we can take first the limit, it's a strict planar limit, we can take in C to infinity while keeping lambda QCD fixed. That's top limit. Or in other words, by keeping the tension of a string fixed. And in this limit, the probability of these events, it goes like 1 over n squared. And one can do some estimate, like some statistics of cross intersections. So what one finds that at finite n, the cutoff scale actually it scales like where really 2D unitarity is broken. It scales like that. So it's not for the lambda QCD, even though kinematically you are allowed to the energies above global mass, you are kinematically allowed to produce the closed strings, produce globules. Really, this production becomes kind of order 1 at this scale, which appears in many other situations. For instance, when people talk about what Midat is doing, kind of some deformed QCD, where you can. So it's kind of this scale. This scale appears there. So the order of limits which one considers, so in other words, kind of at finite n, the function of energy. There are two scales. There is a scale mg for the lambda QCD, or for the string tension, and there is another scale which is n times this. So here, at energies below this scale, we have weakly coupled EFT of goldstone bosons, which is described by the action which I wrote here. So at this scale, the theory becomes strongly coupled, because the scale of the strength of interactions of these goldstone bosons is set by string tension. So here it's strongly coupled, but it's still 2D. So here and here, the theory is still, there is a still two-dimensional subsector which is separated from the rest. And then here, really, physical unitarity is broken. And so here theory becomes four-dimensional. So if I take, then if I take n to infinity limit, if I take this to infinity, then that way I can now consider arbitrary high energies. And so at least I think the zeroth order version of the question what QCD string is to find the description of that two-dimensional theory, UV complete two-dimensional theory, which is obtained by taking this order of limits. So you first take planar limit, and then you can consider arbitrary high energies in the on the world sheet. And what I said before says, well, that this theory it's a hard question because this theory is non-integrable. So yes.
What is n in your EXP?
And that's the number of current. That's
Yeah, but in the EXP description.
well, that's
parameters alpha, beta, gamma, delta.
yeah, it's parameterized. Well, it's not even that, right? Because it controls. Well, in principle, it may control. Those may depend on that, and yeah. So we know, but it also controls. Well, really, kind of as I go to high energies, there are, in addition to two-dimensional excitations, there are also four-dimensional particles. I can add glue balls to my theory, and the main thing which that n does, it parameterizes the strength of coupling of those extra particles which are present in the theory to the string. So was there?
So the point is that if you don't take this large n, you cannot continue this, because there might be a phase condition between nc equal to 3 and large n. So how do you know that whatever you get at the parallel limit will persist also in the largest speed?
No, but first, like the statement that this theory is non-integrable, that doesn't rely on large n. So it's already non-integrable at large n. Well, now then I assume that there is a Hofplanar limit. I assume that there is a limit where the spectrum goes achieves approaches well-defined limit, and that's that's assumption. But yes, it's known. SU3 from SU infinity difference for most global masses is like a delta of 10%. So for most practical purposes, 3, like at least for study globals, 3 is already very, very large. So that's the case. What might have happened is that, as we'll discuss later, then in principle, as we mentioned, there could be additional massive modes on the worldsheet. And what could have happened if, of course, there is no reason for that, but it might have happened that somehow there is a massive mode which would get massless in the large n limit. And that would be the only chance for the theory to restore integrability, because to cancel that particle production, you need to add extra massless degrees of freedom on the worldsheet. And again, that doesn't happen, so there are no extra light states which in large n limit on the worldsheet.
But I mean, okay, maybe formulating the same questions over and over again. But so geometrically, it could be not a string but a rope. So like a thick object.
Well, in the kind of in this effective field theory language, it's just it's a statement about degrees of freedom. Thick.
Right. So. But the rope has additional degrees of freedom, like it could twist, and so those modes could contribute to your.
Well, that we'll discuss it later. The experimental fact is that indeed in D equal 4, actually, I'll talk about it later. But the situation for now is that at D equals 3 in three-dimensional anomalies, actually there is no sign at all of any extra massive modes in the worldsheet. At D equals 4, there is one mode, and it's like a twist. Yeah, it is what you've shown, and it's very easy to understand in gauge theory language because the string is produced by this operator, right? And the local excitation. So if I have a string which kind of goes in z direction, what I can do, I can insert inside. I can either insert kind of FZI, the field strength, which in the kind of lattice language corresponds to deforming string like that. And that's goldstone degree of freedom that present in 3 and 4 dimensions. What I can do in 4 dimensions, I can also insert here Fij. I can insert placket in the transverse direction. And that's exactly has the right quantum numbers to describe the twist. And that's the degree of freedom which is found on the lattice. But yeah, we'll get there later. So probably I should wrap up now, right?
Okay, thank you. People have energy. Is there any more questions? Sergei? No. Anybody back to the UV?
With a question.
Yes.
How did he see that relation where the cutoff scales then?
Well, basically, one makes the following estimate, because for relativistic string, the excitation energy related to the kind of how long the string is.